Why is this not a polynomial? Can anybody help answer that? Yes, so 5 over x can be rewritten as 5 times x to the negative 1, right? So you guys, I'm sure Linda must have told you about the crying baby thing, right? Okay, so when you have an exponent, so that x is a plain old x, right? Which means it's got a little 1 for its exponent. That's imaginary. We're just don't write it down usually. So if I wanted to move that guy up to the numerator, the 1 is positive, which a positive exponent you can equate with a happy baby, right? So if I was going to move it to the numerator, that's going to make an unhappy baby. It's going to start crying, and it's going to make the exponent negative. Okay, so this is going to become 7x to the 4th plus 2x cubed plus 5x to the negative 1. Okay. And a polynomial can only have positive integer exponents, right? So that negative 1 is what makes it not a polynomial, because it's a negative integer. Okay, so I want to divide this quadratic, 6x squared plus 5x minus 6, by 2x plus 3. So there's two things we could do. We could go through the long division, or you could try to ask yourself, you know, what do you multiply 2x plus 3 by to make a 6x squared plus 5x minus 6? The question is probably about long division, so we'll go through the long division. And then we can check it using multiplication. Okay, so the long division of polynomials. It works very similarly to the long division of numbers. So the first thing you look at is just the leading term. Just like when you're dividing two numbers, you look at the highest place value, right? We can think of each term as its own place value. Okay, so you're going to look at just the 2x and the 6x squared, and you would ask yourself, okay, what do you multiply 2x by to make 6x squared? 3x. Good. So I'm going to put the 3x over the 5x because I want to line up like terms, or the way you line up place values when you do regular long division. So 2x times 3x gives you 6x squared. So I'm going to put a 3x right here, lining it up over its like place value. Then you multiply, just like with regular long division. I'm going to take that 3x and multiply it by 2x plus 3. So I have to multiply it by both pieces. So 3x times 2x is 6x squared. 3x times 3 is 9x. And then I have to subtract, just like in regular division. So 6x squared minus 6x squared is 0. What's 5x minus 9x? Negative 4x. And then bring down the minus 6. And then we start the whole procedure again. You ask yourself, 2x times what would give you negative 4x? Close. Negative 2. Negative 2 times 2x is negative 4x. Negative 2 times 3 is negative 6, and you subtract. Negative 4x minus negative 4x is 0. Negative 6 minus negative 6 is 0. So now that we have a remainder of 0, we know we're done. And my answer is 3x minus 2. Forget about what 3? Yeah, when your first step is to just look at the 2x into the 6x squared. Kind of like when you do long division with numbers, like if I gave you, 6,876,451 and asked you to divide by 523,000 or something, like you just match up leading place values, because it's hard to determine if the rest of it will go in. So you just start with the leading place value. And in this case, with polynomials, you start with the leading term. But it's not that we're ignoring the plus 3, because I did multiply by it when I did that part. And then to check, right, if something, so this polynomial divided by 2x plus 3 gives me 3x minus 2. That means to check, I should be able to multiply 2x plus 3 times 3x minus 2, right? I should be able to go in reverse and get the 6x squared plus 5x minus 6, right? Just like if I had done, 30 divided by 6 gives me 5. That means that 6 times 5 should give me 30. Same thing. So when I FOIL this, 2x times 3x is 6x squared. That's first. Outer 2x times negative 2 is negative 4x. 3 times 3x is 9x. And 3 times negative 2 is minus 6. So you get 6x squared plus 5x minus 6, which is what we started with. Oh, okay. So we could have, maybe, if you recognized it, instead of doing the long division out, tried to just factor this guy, and like with our fingers crossed that was one of the factors. This. Okay, so you ask yourself, what would you multiply x by to make x cubed? X squared. So I put my x squared over the x squared term in the dividend, and I say x squared times x is x cubed, and x squared times negative 2 is negative 2x squared. And then I have to subtract that whole thing. So I always use parentheses to remind me that I have to subtract both terms. And a really common mistake is to do negative 5x squared plus negative 2x squared and write negative 7x squared here. Really common. But this minus with the parentheses is to remind you to distribute that negative sign. So this is really negative 5x squared minus negative 2x squared. And minus and negative is the same as adding. So that becomes negative 3x squared. And then just bring down the 8x. And you start again. So you say, what do you multiply x by, right, this guy, to make negative 3x squared? Close. Negative 3x. So negative 3x times x is negative 3x squared. Negative 3x times negative 2 is positive 6x. And then you subtract the whole thing. Negative 3x squared minus negative 3x squared is 0. Those cancel. And then you have 8x minus 6x, which is 2x. Bring down the 4, the minus 4. And then you ask yourself, what do you multiply x by to make 2x? 2. So I have a plus 2 here. 2 times x is 2x. 2 times negative 2 is minus 4. And when I subtract, I get 0. And you can always check a division problem by multiplying, right? So I could also take my x minus 2, multiply it by the result I got, x squared minus 3x plus 2. Multiply those together and you should get the original dividend. How do you multiply those? Just distribute. Yeah, you distribute the x, then distribute the negative 2, then combine like terms. So we'll just do that real quick. So x times x squared is x cubed. X times negative 3x is negative 3x squared. And x times 2 is 2x. So I distributed the x to every term, and then you distribute the negative 2 to every term, and you have negative 2x squared plus 6x minus 4. And then combine your like terms. So I have x cubed. For squareds, I have this one and this one, so that's negative 5x squared. And then for x's, I've got a 2x and a 6x, so that's plus 8x minus 4. That's my original dividend. Okay, so the question is asking us to find all the zeros of the polynomial function And it says, use the rational zero theorem, Descartes' rule of signs, and possibly the graph of the polynomial shown by a graphing utility as an aid in obtaining the first zero. So, rational zero theorem, Descartes' rule of signs, never heard of those, right? They weren't talked about in any of the lectures, not in the packets, right? So, right. But the packets and the lectures did talk a lot about finding zeros of polynomials, right? So let's just do what the packet said, right? So this is something that your textbook covers, these two things that we decided were sort of unnecessary because you can do this without them. So why learn some techniques that are not as helpful? Okay, so we're going to start by graphing this thing. Hopefully we can find one first zero if we graph it. Okay, so maybe I could pull up a graphing calculator, but it doesn't look like Linda has it pinned here. So we graph the polynomial, and the zeros are at -2, 1, and 4. Okay, so let's write that down. We've got it was this function, which may be different than the one you had in your homework because my math lab does like a random, it gives you a different looking function. Okay. So we're done, right? All this asked us to do is to find all the zeros. And we know that there are at most 3, right? And when I graphed it, there were 3 there, so those are all of them. I would give you a picture of the graph. I would say, here's a cubic polynomial, here's a picture of its graph, find all its zeros, right? And the graph might not be as, beautiful as this one. There might only be one spot where you can tell for sure it's got a 0 at, say, -2. So let's just pretend that these were harder to see, or the scale made it so you couldn't tell, or they weren't labeled or something, right? I would say if we know there's a 0 at -2, we can find the other zeros, even if the graph doesn't tell us as explicitly as this graph. So let's just do that for practice. Okay, so, or I could not give you the graph and just say x cubed minus 3x squared minus 6x plus 8 has a 0 at x equals -2. Find all the rest of the zeros, right, with no graph. Or I could give you the graph and you would see that there's a 0 at -2. So if you have a 0 at -2, right, then you also know that it has a factor of what? If x equals -2 is a 0, what do you know has to be a factor of that polynomial? X plus 2. Yeah. Yeah. So imagine if I had set this thing to 0 and solved it. Because it's a cubic, I can factor it into 3 sets of parentheses, right? And then you would set each set to 0. And one of them gives me x equals -2. Right? So that means that x plus 2 had to be in those parentheses. Okay. So that means that x plus 2 would have to be here. So then to figure out what this is, right? What times x plus 2 will give you the original function? You do division. Yeah. So I'm going to do x cubed minus 3x squared minus 6x plus 8 divided by x plus 2. Okay, so you say x times what gives you x cubed? Well, that would be x squared. X squared times x is x cubed. X squared times 2 is 2x squared. Subtract. X cubed minus x cubed is 0. -3x squared minus 2x squared is -5x squared. Bring down the -6x. And then you'd say x times what gives you -5x squared? That would be -5x. -5x times x is -5x squared. Negative 5x times 2 is negative 10x, and subtract. So negative 5x squared minus negative 5x squared gives you 0. And negative 6x minus negative 10x, that's really negative 6x plus 10x, which is 4x. Bring down the 8. X times what will give you 4x? 4. 4 times x is 4x. 4 times 2 is 8. Subtract, and you get 0. So that's the other factor, right? So we now know that x squared minus 5x plus 4 times x plus 2 equals my original function. Sorry, thank you. And then now that it's a quadratic, this one happens to factor. What if it didn't? What if I couldn't factor that? Quadratic formula. Yeah. So anytime you're trying to graph a polynomial, a good place to start is the zeros. And this thing is already factored. So if I set each factor to 0, then I'll get my zeros, right? So here I get x equals 0, and it's multiplicity, what? 2, yeah, because it's a 0 twice based on that degree. X squared x plus 9 quantity squared, well, I would just square root both sides. And that gives me that x plus 9 equals 0. So x equals negative 9. There's no other number that I can plug in there that will make, plug in for x that will make that equal to 0. Negative 9 plus 9 is 0. When you square that, you get 0. The only number that when you square and get an answer of 0 is 0. So x equals 9. And this is multiplicity 1 or 2? Yeah, multiplicity 2 because of the squared. And then here I have x squared equals 3, square root, and I get x equals what? Plus or minus the square root of 3. Yep. And each one has multiplicity 2. So we know the zeros. So 0, 0, 0. Let's look at the leading term. Because the leading term tells us about the end behavior, right? So this way we can get sort of the big picture of what the graph looks like. Well, what's that? If I pretend you were going to multiply this all out, I mean, it would take forever, right? You'd have to do x plus 9 times x plus 9, and that would come out as something quadratic. Then you'd distribute this negative x squared, and then you'd have to multiply all of that by x squared minus 3. It would take a long time. It would be very tedious. But you can imagine if you were to do it, you can figure out what the leading term would be without having to do all of it. Right, so I like to start with anything that has to get squared, right? So I have x plus 9, that has to be squared. If I were to multiply that all out, what would the highest power of x be? I would have an x squared, yeah. Because x plus 9 times x plus 9, you FOIL, you have an x times x, you're going to get an x squared. Okay, so x squared. If I multiply that by x squared, I get x to the 4th. And I have a negative, so it's a negative x to the 4th. And then if I multiply that by this x squared, I'm going to get a negative x to the 6th. So my leading term is going to be negative x to the 6th without having to do all the multiplication, which means my end behavior is going to look like this. The even degree means either both arms are up or both arms are down, and the negative means both arms are down. All right, so I know 3 zeros, and I know the end behavior. So I can plot those things. So we get 0, -9, and plus or minus √3. Zero, -9, and √3, that's like 1.7 or something. Okay, and then my end behavior has to go down from the last 0. I could get a y-intercept, something I could figure out. I would just get that by plugging a 0 in. So that's going to be 0, right? Because this term, when I make that x a 0, doesn't matter what I multiply by, I'm going to get 0. So that's not too helpful. All right, so I know that at 0, I had multiplicity 2, which means it bounces off. Even multiplicity, it bounces. And at √3 was odd, so this goes up, comes down, and bounces off. And then it has to go back through √3. And then 9 was even, which means it bounces. So, I mean, this is a really rough sketch because from what we had, it's impossible to tell how low this piece goes or how high those pieces go. But if you wanted to know, you could just plot a few more points, right? You could just say something between -√3 and -9. I could just say, well, what's f of -5? What's f of -7? √3 is like 1.5 something, I think. Let's check. Oh, 1.73. Okay. So I might do f of 1, f of -1. So I just have my calculator calculate these extra points. That will give me a better idea what the graph looks like. Mm-hmm. No. Nope. Which one? At where? Minus the square root of 3? Okay, so those two at plus or minus √3 have multiplicity 1. Because, okay, so we're looking at this equation. X squared minus 3 equals 0. So I happened to solve it by adding 3 to both sides and then square rooting. But I could factor this thing to be x minus √3, x plus √3. And now each of these is its own equation with no squares in it. Each one has multiplicity 1. This is similar to like if this said x squared minus 9, right? Each of those would have multiplicity 1. All right, so does that help with this? Okay. Okay, so it says we're given a function, this cubic function h of x. It says find one factor graphically, use long division to divide it out, find the zeros of the function, write the function in completely factored form, and then check that you found the correct zeros. Okay. Okay, so I have to find one factor. I have to find one zero graphically. So I'm just going to graph this thing. I'll use GeoGebra again. Okay, so there's my function. So it looks like it has 3 zeros, right? And a cubic will have at most 3 real zeros, right? So this one, I can see it's got 3 real zeros. They show up in the graph, but only one of them is a nice integer that's easy to work with, this -2. These other 2 are either fractions or, even worse, they're radicals with square roots in them or something. But this one is nice, right? A nice, clean integer, -2. All right, so we have a 0 at x equals -2, right? Which means it has a factor of x plus 2. X minus -2. So all factors are always x minus the 0. So x minus -2 gives you the x plus 2. So then we divide to find another factor. So I'm going to do x cubed minus x squared minus 5x plus 2 divided by x plus 2. Okay, x times what gives you x cubed? X squared. X times x squared times x is x cubed. X squared times 2 is 2x squared. Subtract. X cubed minus x cubed is 0. Those cancel. Negative x squared minus 2x squared is -3x squared. Bring down the -5x, and we start again. X times what would give you -3x squared? -3x. -3x times x is -3x squared. -3x times 2 is -6x. Subtract. -3x squared minus -3x squared is 0. -5x minus -6x is x. So x times what gives you x? 1. Times x is x. 1 times 2 is 2. Subtract. No remainder. So where? Say that again. If you had a negative right here, that can happen. Yeah. Nothing. It's just part of your result. Yeah, one of them just has a negative leading coefficient. You could, yeah. Yeah, you could factor it out if it makes you uncomfortable. So, like if I had, no, you're right. It's not common to have a negative leading coefficient. Many people would just go like this. Factor out a negative, reverse distribute the negative, so that you can deal with the negative sign separately from the factor. Okay, so I now know that h of x, this function, factors to this times this. So h of x, which is this cubic polynomial right here. I now know factors to x plus 2 times x squared minus 3x plus 1. So now what do I do to find my other two zeros? I know one of them's at -2. Quadratic formula. Use the quadratic formula on the x squared minus 3x plus 1. So we have x is -b, so that would be 3, plus or minus the square root of b squared, 9, minus 4 times a times c all over 2a. 9 minus 4 is 5. Oops. Over 2. Those are my other two zeros. 3 plus root 5 over 2 and 3 minus root 5 over 2. All right, so let's look at the rest of the question. So for 1c, it asks for the leading coefficient. So I'll just write this down again. One, right? The coefficient on the leading term, x cubed, is a 1. The degree, what's the degree? 3, yep. The number of x-intercepts, 3. We saw that when we graphed it. The zeros, we just found those. We had one at -2, and then the other two are at 3 plus or minus root 5 over 2. So if I was going to write this thing in completely factored form, my leading coefficient is 1, and then each of my zeros becomes a factor of x minus it. My completely factored form. All three of these factors are linear. Right, because linear just means that the degree on x in each of these guys is there's a hidden little 1 there. Yeah, it's always x minus whatever the 0 is. So if the 0 happens to be negative, like with the -2, it comes out positive because that's really x minus -2. Okay, one more. Class 29, number 12. Okay, so that's class 30. Oh, yeah, mine, everyone has slightly different numbers. Yeah. Okay, so the width is x plus 0.6, and the area is this cubic thing. So we know that area, oops, is equal to length times width, right? And we know the width. So we have some length times x plus 0.6. And that should give me this cubic, which I didn't leave enough room to write out. So my area is 0.4 x cubed minus 0.06 x squared equals my length, unknown, times my width, x plus 0.6. So if I wanted to solve this thing for length, what would I do? Divide by x plus 0.6. So I have to do a long division. Right? I'm going to have to do that 0.4 x to cubed, blah, 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 divided by x plus 0.6. Minus 0.06 x squared. I think that was it. Plus 0.02x plus 0.12. Okay, so what would I multiply x by to make a 0.4 x cubed? 0.4 x squared. Yeah. So 0.4 x squared times x is 0.4 x cubed. 0.4 x squared times 0.6. 0.4 times 0.6 would be 0.24 x squared and subtract. Is that right? 0.4 times 0.6? Okay. All right, so these guys cancel. And then I have negative 0.06 minus 0.24, which I think is going to give me negative 0.3. Negative 0.3 x squared, bring down the 0.02 x. All right, so x times what would give me negative 0.3 x squared? Negative 0.3 x. Distribute, and I get negative 0.3 x squared. 0.3 times 0.6 is 0.18. And subtract. Those cancel. 0.2 minus negative, oh, sorry, 0.02 minus negative 0.18 is 0.2, I think. 0.2x, bring down the 0.12. X times what gives you 0.2x? 2. Distribute. Subtract. Remainder is 0. No remainder. You got a remainder? You probably made a mistake. So why don't you, yeah, read it off to me. What division were you doing? So you didn't have any decimals? That's okay.